What is up, engine heads? In today's video, we'll be taking a very detailed, in-depth look at the inline two-cylinder engine, and we'll be doing a detailed comparison of its three most widely used configurations: 360, 180, and 270 degrees. Although this is a long video, I have split it into chapters for your convenience, and although it does cover some pretty complicated mechanical concepts, I promise that the explanation is very organic and can be understood by pretty much everyone. And I also promise that by the end of this video, you will have the satisfaction of a newfound appreciation for the reciprocating piston engine. So, let's get started. First, just to clarify something: inline twin, parallel twin, straight twin, interchangeable terms. They mean the same thing. They mean that we have two cylinders right next to each other, in line with each other, parallel with each other. The two cylinders are pointing in the same direction, and thus they can share a single cylinder head. Obviously, the only other two-cylinder configurations are the V-twin and the boxer twin. In the case of the V-twin and the boxer twin, the cylinders are pointing in different directions, and thus they cannot share a single cylinder head. They need two cylinder heads and two sets of valve trains. So let's start with a 360-degree inline two. In the case of this engine, both of the pistons move up and down together all the time. Examples of vehicles using this engine would be all the older British bikes from the 30s and onward, of course, including the Triumph Bonneville. We also have the BMW F800 range, the Kawasaki W800, and we also have a car engine using this configuration, which is, of course, the Fiat Twin Air engine used in the Fiat 500, among others. The 360 degrees refers to the firing interval of the engine. We fire the first cylinder, rotate 360 degrees or one full revolution, then fire the second cylinder, again rotate 360 degrees, fire the first cylinder again, and so on and so on. Obviously, this means that the engine has an even firing interval of 360, 360, 360, and as we know, an even firing interval positively contributes to engine smoothness. Next up is the 180 degrees inline two. In this case, we have 180 degrees of separation between the two crank throws, which means that when one piston is at top dead center, the other piston will be at bottom dead center, and as the engine is running, the pistons will always be reciprocating in opposite directions. Examples of motorcycles using this engine include a bunch of different Japanese bikes from the 60s, and modern day examples are the Ninja 650 as well as the Yamaha R3. When it comes to the firing interval, it goes like this. We fire the first cylinder, rotate 180 degrees, and then we fire the second cylinder. Obviously, because we're talking about four-stroke engines here, when the second cylinder fires, it means that the first cylinder has just completed the power stroke and it's starting the exhaust stroke. And it has to complete the exhaust stroke and then do intake and compression before we can fire the engine again. Each stroke is 180 degrees, which means that we need to rotate the engine another 540 degrees before the engine can fire again, resulting in an uneven firing interval of 180, 540, 180, 540. Next up, we have the 270 degree inline two, and this is probably the most widespread modern day configuration. We have it in the Africa Twin, the new Africa Twin, and a bunch of other Honda bikes, the new Aprilia stuff. We have it also pretty much in the entire Triumph range starting from 2016, the new BMW F900 range. It's also in the Yamaha MT-07 and all the other Yamaha bikes using the CP2 engine. It's also in Royal Enfield bikes and many, many more. When it comes to the firing interval, we fire the first cylinder, rotate the engine 270 degrees, fire the second cylinder, and now again we're speaking about four-stroke engines, so when we fire the second cylinder, the first cylinder will have completed only half of its exhaust stroke. So to fire the engine again, we need to complete the other half of the first cylinder's exhaust stroke, which is 90 degrees, and then the first cylinder has to do intake and compression before it can fire again. So we have 90 plus two strokes of 180, which results in 450. The result is an uneven firing interval of 270, 450, 270, 450. Although the firing interval is uneven, it is less uneven than that of the 180 degrees inline two. Also, the 270 degrees inline two shares its firing interval with the V-twin engine, which is why the two have a pretty similar soundtrack. So here we have a visual overview of the firing intervals of the three engines. Obviously, the 360-degree engine is the smoothest in this regard, but we have to remember that gaps between engine power pulses are transmitted to a motorcycle tire via a chain, belt, or shaft. And we have learned in our past Yamaha crossplane video that these longer periods of engine silence can translate into recovery gaps for the tire, helping the tire re-grip at the limit of traction and during low traction situations, making the bike more controllable and easier to handle in these scenarios. This is also one of the reasons why uneven firing Harley-Davidson motorcycles dominated flat track racing for so long. Although the firing interval is important, it is only one piece of the overall engine balance and engine character puzzle. And to better understand these engines, we'll have to explore their primary and secondary engine balance. Now, I have covered these concepts in the past, and even though inline two-cylinder engines have the least number of cylinders of all the engines we have covered so far, to truly understand them, we'll have to take a much deeper dive into primary and secondary balance in this video. But don't be afraid, as always, it's going to be intuitive and organic and easy to understand. When an engine experiences a primary imbalance, this creates first-order vibrations. Now, this isn't what's important to remember. What's important to remember is that when we have primary vibrations, they always occur as a consequence of the mass of the piston moving up and down in the cylinder. Now, as the engine is running, the piston is constantly accelerating and decelerating. But before we get into the exact motion of the piston, of the acceleration and deceleration, what it means for engine vibrations, we first have to have a good basic understanding of the concepts of acceleration, velocity, and force. Although in day-to-day usage, when we say acceleration, we imply that we're speeding up. In physics, acceleration means the rate of change of speed. It doesn't matter if you're speeding up or slowing down. What matters is the rate of change of speed. How fast, how quickly your speed is changing. The higher, the faster the rate of change of speed, the higher the acceleration and the higher the force. When you're driving a car and you accelerate hard, you will feel a force acting on your body. The higher the acceleration, the higher the rate of change of speed, the higher the force acting on your body. But also, if you decide to start braking hard, there will be a force acting on your body. The harder you brake, the more you slow down, the higher the rate of change of speed, the higher the force acting on our body. So if we're speeding up and slowing down at the same rate, if we're increasing and decreasing speed at the same rate, the magnitude of the force will be the same in both cases. However, what is affected by this is the direction of the force. The direction of the force acting on your body when you're speeding up is opposite the direction of the force acting on your body when you're braking hard. The final important thing to remember when it comes to these basics is that acceleration is the rate of change of speed, which means that it doesn't matter how fast you're moving. If you're not changing your speed, force will be zero. So you could be sitting in a car traveling at 300 kilometers per hour. If you're not accelerating or if you're not braking, the force acting on your body will be zero. So if speed is constant, that means that there's no rate of change of speed, and it means that acceleration is zero, and force is mass times acceleration, and anything multiplied by zero is zero. And again, you can experience this when you're driving in a car. If you're keeping a constant speed, you will feel no force acting on your body. Now, the best way to see how the piston's acceleration and deceleration influences the forces generated by the piston is to plot the movement of the piston on a graph. So on our horizontal axis, on our bottom horizontal axis, we have degrees of crankshaft rotation starting from TDC and doing one full revolution until we see TDC again. Now our upright vertical axis is the force generated by the piston, and this line, horizontal line, represents the net zero force generated by the piston. This is what we want, because when there's net zero force generated by the piston acting on the engine, then there's also no vibrations created by the piston. And the force generated by a single piston over a single engine revolution looks like this. So let's explain this graph. Now obviously our piston mass is constant, meaning that the only thing influencing the forces generated by the piston is the acceleration. So starting from TDC, from top dead center, the piston is completely still. For a very, very brief moment of time, the piston stops. And then starting from TDC, moving downward, the piston accelerates hard down the bore. At this point, the force is high because the acceleration is high. The acceleration is high because the rate of change of speed is high. The rate of change of speed is high because the piston started moving from zero velocity and then rapidly reached a very high velocity. Continuing towards 90 degrees of engine's rotation, we can see that the piston hits a point when the force generated by the piston is zero. This is because somewhere around this point, the piston reaches maximum velocity, and it maintains this maximum velocity for a very brief point of time. Because there's maximum velocity, the piston isn't accelerating and decelerating, meaning that the net force is zero. Now, just to be clear, in most engines, the piston will reach maximum velocity a bit before 90 degrees of rotation, but for the sake of simplicity, we'll ignore this. But obviously the moment of maximum velocity lasts a very short amount of time, and right after this the piston starts slowing down as it prepares to again make a stop at bottom dead center. Because we're now slowing down instead of speeding up, the direction of the acceleration changes in the same way as it changes when we transition from accelerating to braking when driving a car. The opposite direction of acceleration is represented by a negative number, and of course multiplying a number with a negative number results in a negative number, and this is why the changing direction of acceleration also changes the direction of the force. As the piston reaches bottom dead center, you can see that the force exerted by the piston onto the engine peaks at both the bottom and top dead center. A very intuitive way of understanding why and how this happens is to simply take your smartphone and try to move it very rapidly up and down. So move it to a position up and then move it down as fast as possible to simulate what the piston is doing. So when you reach the topmost position of travel with your hand in your phone, you have to change direction rapidly and move the phone downward. This is the same thing that the piston is doing at TDC. It reaches TDC and then the con rod yanks it hard by the piston pin to pull it down and change its direction. When you do this with your phone, you can feel that as you try to push the phone down, you have to overcome the force of the phone, the inertia of the phone, because the phone wants to keep traveling in the same direction. It wants to fly outward from your hand, keep going up, but you have to overcome this with your hand by keeping a firm grip on the phone. And in the same way that the phone exerts an upward force on your hand as you force it to change direction, so too does the piston exert an upward force on the engine when it changes direction at top dead center. In fact, the piston wants to keep traveling upward and smash into the cylinder head, but the connecting rod yanks it by the piston pin and pulls it down, forcing it to change direction. Just like the phone, the piston also has inertia, and it exerts a force in the direction in which it was traveling before it was forced to change direction. And if we expand our graph, we can see that this is clearly represented on it as well. The force peaks at bottom and top dead center when the piston is forced to change direction, and this is when most force by the piston is exerted onto the engine, causing it to vibrate up and down as the engine is running. Now we have to remember that the mass and the forces created by the piston cannot be counteracted by the crankshaft counterweight. When the piston's at TDC, the crankshaft counterweight does indeed oppose the piston and it can counterbalance it. But as soon as the engine position changes, and for example when the engine is at 90 degrees, we can see that the piston and the crankshaft counterweight are now pointing in different directions, which means that the counterweight cannot cancel out the forces generated by the piston. Instead, the counterweight only cancels out the mass of the crankpin and the big end of the connecting rod, while the mass of the piston can only be cancelled out by the mass of another piston. So to cancel out the forces of our single piston on the graph, let's superimpose another piston on top of it. But the other piston will be doing the opposite thing of what our first piston is doing. So they'll have the same mass, which means they'll have the same force magnitude, but their forces will be opposite in direction. And so the two pistons will be cancelling each other out, resulting in a net force of 0. And what you have right here on this graph is a 180 degrees inline two-cylinder engine. So as we know, in 180 degrees inline twin, when one piston is changing direction at BDC, the other piston is changing direction at TDC, which means that they're exerting forces of equal magnitude but opposite direction onto the engine. So of course the two forces cancel each other out, and the net primary force or the primary imbalance in the 180 inline two is 0. In stark contrast to this, the 360 degree twin has two pistons moving together. So when two pistons are changing direction together at TDC, they're doing the same thing at BDC, which means that the two pistons are exerting forces of equal magnitude, but also of equal direction onto the engine. So instead of canceling each other out, the forces actually stack up, they double up. So the 360 degree twin has horrible primary balance and the 180 degree twin is perfect. Well, it's not that simple because the 180 degree twin also has a problem when it comes to primary balance. As we said, there's two forces, equal in magnitude and opposite in direction. However, the two forces aren't directly opposing each other. There's a perpendicular distance between the two forces, and this creates a rocking couple. And by definition, this is what a rocking couple is. Two forces, equal in magnitude, opposite in direction, displaced by perpendicular distance. And to visualize the effects of a rocking couple, you can take any square object and use your hands to apply two forces that are equal in magnitude but opposite in direction at the ends of the object. And you will see that the object will try to rotate. And this is exactly what the rocking couple does to the 180-degree inline twin. Instead of shaking it up and down violently like it does in the 360-degree twin, it's trying to shake the engine like this. Now when it comes to the primary vibrations of the 360-degree twin, they must be engineered out of the engine, because if they were left unattended, they do have the potential to actually destroy the engine over time. And the only way to get rid of these vibrations is to use either a single massive balancing shaft or twin balancing shafts to counter the forces of the two pistons. And although this does get rid of most of the vibrations, it is a bit undesirable because it adds complexity, moving parts, cost, weight, and friction into the engine. When it comes to the rocking couple vibrations of the 180-degree inline twin, they're usually less apparent to the rider, especially if the engine isn't a stressed member of the chassis. And if the engine is small enough and doesn't rev high enough, sometimes you could even leave these vibrations unattended. However, most manufacturers will choose to balance out the rocking couple vibrations out of the 180-degree inline twin. In most cases, in practice, this is a bit easier to do. They're a bit easier to engineer out of the engine when compared to the massive primary vibrations of the 360-degree inline twin. So what about the 270-degree inline twin? Well, when it comes to primary balance, it actually strikes the middle ground between the 360 and 180 degrees inline twin. As we know, in the 270-degree twin, the one piston trails the other by 90 degrees. And we can actually plot this, we can superimpose the second piston on top of the first piston on our little graph. And as you can see, the forces aren't canceling each other fully. They're capable of canceling each other out only partially, which means that some primary imbalance does stay. And although the final resulting primary imbalance isn't as bad as in the 360-degree inline twin, it still needs to be engineered out to reduce vibrations. Now let's talk about secondary balance. And when it comes to the secondary balance and the second order vibrations that they create, they are a consequence of the relationship between the piston and the connecting rod, the geometric relationship of these two items. Now, when the engine is at TDC, the connecting rod is obviously fully upright. Now, when the engine rotates to 90 degrees of rotation and to 270 degrees of rotation, we can see that the connecting rod is no longer upright. It is now at an angle. This means that the length of the connecting rod in relation to the piston and the crankshaft changes as the engine is running. Obviously, the absolute length of the connecting rod stays the same. If your connecting rod gets longer, your engine is probably toast. It's a solid metal item. However, the relative length in relation to the piston and the crankshaft does change. So when the engine rotates from 0 TDC to 90 degrees of rotation, the connecting rod is going to get angled. And as it does this, as it shortens, it's going to pull down the piston an additional distance. It's going to accelerate the piston. It's going to add acceleration onto the already present acceleration of the piston. In the same way, when the engine rotates from 90 to 180 degrees to bottom dead center, the connecting rod is going to reassume its upright position, which means that it's going to slow down the piston, it's going to push it up, and it's going to take away a bit of acceleration from the main acceleration of the piston. Obviously, any object can see only one acceleration. It can have only one acceleration value. However, for the purposes of clarity and better understanding secondary balance, we will observe the acceleration created by the movement of the connecting rod separately from the overall acceleration of the piston. And this acceleration too and the forces resulting from it can also be plotted on our little graph, and they look like this. When observing this graph, it's a good idea to forget about the main movement of the piston, the up and down thing. Only think about what the connecting rod is doing to the piston. When is it accelerating and when is it decelerating the piston? This is what's important. And from this graph, we can see that whenever the connecting rod is straightening, when it's assuming its straight position, it's slowing down the piston. Whenever the connecting rod is angling, it's speeding up the piston. In other words, whenever a piston is coming to a stop, whenever it's reaching top dead center or bottom dead center, it's slowing down, meaning that the forces created by secondary balance point the same way at BDC and at TDC, unlike the forces from primary balance, which point at different directions at bottom and top dead center. Obviously, secondary forces are smaller than primary forces because the acceleration created by the connecting rod is smaller than the main acceleration of the piston. This means that if the engine doesn't have a sufficiently high RPM and/or displacement, secondary forces can be left unbalanced. They can be ignored. And this is the case in practice with many motorcycle engines because they aren't very high in displacement. And in practice, secondary balances won't be apparent or annoying to the rider, and they won't be damaging to the engine. Despite this, secondary vibrations definitely do exist, and they are a design concern when it comes to engine development, and they do ultimately influence the character of the engine. Now, the 360-degree and 180-degree inline twos actually both suck when it comes to secondary balance, and they both suck equally. How come? Well, the deal is that in both of these engines we have two pistons coming to a stop at the same time. And as we said, for secondary balance, it doesn't matter that one piston is approaching TDC and the other is approaching BDC. Because as we know, when the piston is approaching top or bottom dead center, in both of these cases, the connecting rod is reassuming its upright position. It's becoming upright again, which means that whenever the piston is approaching BDC or TDC, the connecting rod is slowing it down, which means that secondary forces always point upright both at BDC and TDC. And because we have two pistons in both of these engines, it means that the secondary forces actually stack up and increase the secondary imbalance. And even though secondary forces aren't that strong, it pays to get rid of them if the engine is sufficiently large. For example, this 800cc 360-degree inline twin from BMW, which can be found in the F800 series, uses a dummy connecting rod and an oscillating link to address both primary and secondary forces. And even though this is a clever mechanism, and even though Ducati used something similar in their Supermoto engines, and some other engines also use dummy connecting rods and oscillating links and similar systems, and even though these do a great deal for engine balance, they still obviously add a lot of complexity, moving parts, and friction onto the engine. So what about the secondary balance of the 270-degree inline two? Well, as we said in this engine, when one piston is approaching top or bottom dead center, the other piston is going to be at halfway off its stroke, meaning that when one connecting rod is assuming its upright position, the other connecting rod is assuming its angle position, meaning that one connecting rod is accelerating the piston and the other connecting rod is decelerating the piston, meaning that the forces from this are pointing in opposite directions. So we have the same force magnitude, but opposite direction, meaning that the forces cancel each other out, and the 270-degree inline two has perfect secondary balance. But again, we have the same problem as with the primary balance of the 180 degrees inline two, because although the forces are of the same magnitude and opposite direction, there is a perpendicular displacement between them, which means that the 270-degree inline two has a secondary rocking couple. But as we already said, secondary forces are pretty small, and the rocking couple is usually almost non-apparent, which means that most 270-degree inline two engines do not need any extra engineering to get rid of the secondary rocking couple. So let's sum up the balances. When it comes to primary, the 360-degree is the worst, the 180 is the best, and the 270 is somewhere in between. When it comes to secondary balance, 270 is the best, and 180 and 360 equally suck. So why is the 270-degree inline two so popular nowadays? Well, there's many reasons. First of all, its primary imbalance isn't that bad, and it isn't hard to engineer it out of the engine, and its secondary balance doesn't really need any engineering at all. And although the primary balance isn't as good as with 180 degrees inline two, most market research shows that the pulsations created by the firing interval and the imbalance of this engine are actually found pleasant by most consumers. Another factor is the soundtrack. Although engine sound is a very subjective thing, most market research again shows that many people prefer the uneven, syncopated soundtrack of a V-twin, and this is exactly what a 270-degree inline two emulates to a great extent. But the benefit is that the inline two doesn't have the packaging concerns of a 90-degree V-twin. It's a lot easier to fit two cylinders that are right next to each other inside a motorcycle frame than it is to fit a 90-degree V-twin. On top of this, it's easier and cheaper to manufacture because an inline two can use a single cylinder head and a single valve train, which also means that it has less friction than a V-twin, which needs two cylinder heads and two valve trains. So essentially we're getting the soundtrack and the feeling of a 90-degree V-twin with the compactness and cost effectiveness of an inline two. Another key benefit of this engine is that there is never two pistons coming to a stop at the same time, meaning that the crankshaft speed in a 270-degree inline twin fluctuates less than in the other two inline two designs. Obviously, crankshaft speed is slowest at top dead center and bottom dead center because this is where the crankshaft has to slow down to accommodate the changing direction of the piston. However, in the 270-degree inline two, one piston is always mid-stroke, which means that the crankshaft speed doesn't fluctuate as much. And the benefit of this is a smoother, more even torque delivery, which also gives the rider the feeling of a more direct throttle control over the engine. And because the crankshaft speed is more even as the engine runs, it means that this engine needs less flywheel mass to smoothen out its power pulsations. Less flywheel mass means less engine inertia, and this means that when you release the throttle, there's a lot of engine braking, and you do not need to use as much braking with the brakes to slow the bike down when you release the throttle, and this is a feeling preferred by many riders. The 270-degree engines also develop their peak torque lower in the rev range, which makes the bike more usable in real-world condition and make it seem more lively. Compared to this, the 180 and 360-degree engines develop their peak power and torque higher up in the rev range, so the engine needs to be revved out more to get the bike going. So as you can see, the 270 has many benefits, which explains why it's so popular. On the other hand, the 360 engine, for example, has a primary imbalance which can create an annoying buzzing vibration, which is disliked by many riders. Now, the key advantage of the 360 engines, which explains why they were so popular in the past, is that the two pistons are moving together all the time, which means that you can feed the two cylinders with a single carburetor and use a single inexpensive ignition system to ignite both of the cylinders. Of course, these factors are much less relevant today with modern technology. One of the key disadvantages of the 360 engine is that it has the highest crankcase-related pumping losses. As you can see, as this engine is running, the volume of the crankcase is dramatically changing. The engine has to work against this because it constantly has to compress the fluids inside the crankcase. Of course, this negatively impacts fuel efficiency, and it makes it harder for this engine to achieve high RPM. On the other hand, the 180 degrees inline 2 is a champion when it comes to crankcase-related pumping losses because as this engine is running, the crankcase volume remains pretty much constant, which is why this engine has the lowest crankcase-related pumping losses, and this is why it's often used in bikes that need to achieve a high redline. And there you have it. Those are the main differences between the three most popular configurations of the inline 2-cylinder engine. I hope you enjoyed this video, found it useful and informative. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.